Okay, we're now officially recording. So I'm going to share my screen uh, just to kind of show you guys what's in Schoology and explain what we're going to be doing on today. So obviously we are talking about Newton's laws of motion, forces, and dynamics, which is the topic of this second unit. Just so you all know, we're going to have a 6-week test on Thursday of next week. So just something to keep in mind. There will be a 6-week test on Thursday of next week, and the test will cover both information from both units, the units on kinematics and also this unit on forces and dynamics. So just something to keep in mind. Today, we're going to talk more about forces, but we're going to focus on a specific force known as the normal force. So if you click on the folder for today. Today's a Thursday. So click on the folder. Okay. So we're going to explain a few things about the normal force first. We're going to do several examples. And of course, as soon as I release you guys, you guys can get started on your assignment, which is titled the normal force, and it's about 16 multiple choice questions. Okay. Now, before we get started with talking about the normal force, there's something that I want to review briefly that I talked about with you guys on last time, and that is how to calculate weight. Okay. So, remember me saying last time, if you're standing here on Earth and you want to know your weight here on Earth, all you have to do is step on a scale, and the scale tells you your weight. Well, anytime you're standing on a scale, guys, what exactly is the scale registering? Well, think about it like this, guys. Think logically here. The reason why you're able to stand on the scale is because gravity keeps you pulled downward toward the scale. Like, in other words, gravity keeps you glued to the scale because gravity pulls you downward. So, in some indirect sense, the scale is actually measuring the force of gravity, okay, because gravity is responsible for pulling you downward. So remember what I said last time, guys, that weight, whatever your weight is equivalent to the force of gravity acting on you. And again, we're talking about, weight in newtons, not necessarily in pounds. Okay. In this class, we use newtons for weight. Okay. Now, what is the equation for the force of gravity? I gave this to you guys last time. And someone tell me, what is the mathematical equation for the force of gravity? Anyone? It's mass times what?
Acceleration.
Well, mass force equals mass times acceleration. That's the general form of Newton's second law. Like, force is equal to mass times acceleration. But when I'm specifically solving for the force of gravity, it's mass times what? Exactly. Thank you, Jade. I saw you put in the chat box. Mass times 9.8. Now, guys, you know what? I tell you what. In order to make your calculations easier for this um, topic and for this assignment later on, let's just round 9.8 off the 10. That way, our calculations will be really easy. We're going to round 9.8 off the 10. So, guys, if I have this block here, and this block is sitting on the surface of this table, and let's say this block has a mass of 2 kilograms. In this case right here, what is the force of gravity acting on this block? Or in other words, what is the weight of the block here in blue? 2 times 10 is just 20. So 20 newtons of force is the weight of the block. In other words, that's how much gravity is pulling downward on this block here. So the force of gravity is 20 newtons of force, which is equivalent to its weight. Okay, so keep that in mind, guys. That's something that's important, that you guys know how to use this equation here to calculate the force of gravity acting on your object, because that's going to appear a lot in this course. Okay. So now, on today, we are going to be focusing on the normal force. Okay? So, what exactly is the normal force? Well, guys, this term normal here is actually a mathematical term. And guys, normal, in terms of its mathematical definition, just basically means perpendicular. So the normal force is a perpendicular force. So what exactly causes the normal force? Well, let me just show you guys and give you guys an example. So guys, the normal force arises whenever two objects are in direct contact with each other. So one object is pressing against the other, and the other object presses back. So, for example, let me explain what I mean by that. Guys, imagine for a second that I have a book here, a blue book sitting on top of a white book. Okay, so um, um, guys, as um, as the blue book sits on top of the white book, um, can someone tell me right now how many forces do you think right now are acting on top of the blue book, or how many forces are acting on the blue book? Does anyone know? Just looking at it, how many forces right now do you think are acting on this blue book? Remember, it's not moving; it's at rest. Okay, so as actually more than one, guys, because we know for sure gravity is acting on the book, right? Gravity is acting on the book because remember, gravity is first responsible for pulling it downward, right? So the force of gravity is pulling the book downward to the center of the earth. But obviously, right now, if you're looking right now at the book, it's obviously not accelerating downward. So something else is happening. Yeah, the bottom book exactly. So yeah, so that's actually two forces. So there has to be another force to balance gravity. So the bottom book is pushing up on the top book, on the blue book. Okay. So guys, that force, the force from the bottom book pushing up on the blue book, we call that the normal force. Okay. So right now there are two forces acting on this blue book. There's gravity pushing downward, okay, but then there's another force balancing that. There's the top book. The surface of the top book literally pushes up on the blue book, and those forces are balanced. And we know those forces are balanced because right now this object is not moving; it's at rest. It's not accelerating. Okay, so since it's at rest, we have two forces that are in balance. Again, guys, that force is called the normal force. And here's the reason why we call it the normal force because, guys, anytime you have two objects that are in direct contact with each other, the normal force is always perpendicular to the surface of contact. So since this is our surface of contact right here, normal force is pointed straight up. It's pointed perpendicular to that surface. Okay? So we have two objects, one presses against the other object, and if the blue book pushes on the bottom book, so the blue book pushes on the white book. Remember, Newton's third law says the white book must push back up on the blue book, and we're going to call that force the normal force because these two objects are in direct contact with each other. One presses against the other. So hopefully that makes sense. Let me share my screen here. Because there's like a short 3-minute video that I linked to in Schoology, which links you to YouTube. And it does a really good job introducing the normal force. So let me play that for you guys now.
Now we can consider the normal force. So our first question is, what do we mean by normal force? Let's start with one word at a time. Force, we've already talked about, is a push or pull on an object. So then we get to normal. Now what we don't mean by this is it's not an ordinary force. While they happen all the time, that's not the usage of the word normal we mean. Instead, we're talking about a mathematical definition of normal that refers to the perpendicular. So for example, if I have a surface, my normal force is always going to be at a 90-degree angle perpendicular straight out from that surface. And I use the F with a sub n as my symbol for it, both capital F and capital N. So here's some examples. Again, if I have a horizontal surface, my normal force might be straight up from that surface. If I have a vertical surface, my perpendicular is going to be, say, out to the left. And if I have a sloped surface, my normal force is still going to be perpendicular, but that means it's going to be off at an angle. Now, when do you have the normal force? Anytime you have solid surfaces in contact with each other. The normal force is the force that prevents those solid objects from going through each other. Now, from Newton's third law, we know that forces come in pairs. So let's understand that in terms of a normal force. The ground pushes up on the block with a normal force, but the block also pushes down on the ground. If I push on the wall to the right, the wall pushes back on me to the left. These are force pairs. I push on it, it pushes back on me. In both cases, I can't push through the wall and the wall doesn't push through me. Now, if I've got multiple surfaces, like I have in this example, I have to consider a normal force for each one of the points of contact. So for example, up here at my hands, I have a normal force where I'm pushing on the wall and the wall is pushing back on my hands. In this case, my front foot is going to have a second normal force where my foot pushes down on the floor and the floor pushes up on that front foot. And in the back foot, we have a third normal force. And again, it's a force pair where my foot pushes down on the floor and the floor pushes back up on my foot. If I have multiple objects, I need to consider the surfaces for each one of those objects. So here I've got two boxes sitting on top of each other, sitting on the floor. Well, there's a surface between the two boxes, and so the green box pushes up on the blue box, but the blue box is also pushing down on the green box. And there's a surface contact between the green box and the floor, so that the floor pushes up on the green box and the green box pushes down on the floor. When I go to do force diagrams, remember that I want to treat each object separately. So my blue box has a normal force upwards due to the green box, and my green box has two normal forces, one due to the floor and one due to the box sitting on top of it. Now don't forget, both of those boxes also have a force of gravity, assuming they're sitting here on Earth and not out in space. And so your full force diagram would have to take into account not just the normal forces, but any other forces that are on there as well. So that's your introduction to the normal force.
Okay, guys, so hopefully that made sense to you guys. The normal force. What I'm going to do, I'm going to spend the rest of the class time just working out examples so that whenever you guys are working on your assignment today, you should be pretty comfortable with how to find the normal force in various situations and using varying masses. Okay, so that's what we're going to do now. Okay, so guys, let me give you guys an idea how your problems could look like on your assignment for later on. So I can give you an object here, such as a blue box, and I can tell you, let's imagine this blue box, like say it has a mass of 3 kilograms. Okay, and I would ask you to find what right now is the magnitude of the normal force. What is the magnitude of the normal force right now acting on this surface here, acting on the blue box? Well, guys, in order to do these problems, what you want to do, you want to draw all the forces first for your force diagram, and then logically go through what has to be your normal force. So right now, we know that there are two forces acting on this blue box. There's gravity pulling it downward, but there's also the surface of the table pushing upward on the blue box. And we know those forces have to be in balance because the object is not moving. It's at rest. It's just sitting there. So I'm going to draw one force downward. That's the force of gravity. I'm going to draw one force upward. And that's the normal force. And again, I did my best to try to keep these arrows equal to demonstrate that, those forces are in balance. Okay. So, and before we can figure out the normal force, we need to figure out what is the magnitude of the force of gravity. Remember, the force of gravity the equation for the force of gravity is just mass times 9.8, where I'm going to round 9.8 out to 10 to make my calculations easier. So if my mass here is 3 kilograms, guys, that means my force of gravity must be what? Anyway? Yes, thank you, Courtney. 30 newtons. Now, guys, to be specific, since this arrow is pointed downward, technically that's a negative 30 newtons. And of course, if this is negative 30 newtons, that means what has to be the value of the normal force to balance that? That means the normal force has to be positive 30 newtons. So that's easy. Hopefully that should make sense to you guys. For this problem, that's how you figure out what is the magnitude of the normal force. Here, the normal force is going to balance gravity because the object is at rest. And by the way, guys, just so you know, for this assignment for today, it really won't be necessary for you to write positives and negatives. But just know in the future, it's going to be a good idea to do that because forces can be negative. Because with forces, direction is important. But today, I'm not going to worry about writing the positive and negatives. Just know that, guys, if an arrow is pointed downward, just know that is a negative force. Okay, and it's pointed upward, we're going to use the convention of calling that a positive force. Okay. Let's do one more simple example like this before we move on to some examples that are a little bit more complicated. Okay. So for this example here, so what if I tell you that you have a red box which has a mass of 7 kilograms and it's sitting on the table, and I ask you to find the magnitude of the normal force. Okay. It should be easy. In this example here, we know that we have gravity. We know we have gravity acting straight downward. And we know we have the surface of this table here pushing up on the red box, and it's balancing gravity because the box is at rest, it's not moving. So if this force right here, if this force is basically mass times 10, in other words, 7 kilograms times 10 gives me 70 newtons. And again, that's a negative, just so you know that, because it's pointed downward. If that's a negative 70, that means the normal force here has to be a positive 70. So that's how you find a normal force in that situation. Let us go to a situation that is a little bit more complicated. Suppose I tell you that an object is sitting on a surface here. So we imagine we have a blue box, and this blue box is sitting on the surface. And let us imagine that this box here has a mass of 5 kilograms. Okay? And let us imagine that something or someone is already pushing downward on this box with some force. So some force that looks like this. And guys, I'm going to say that this force here is 10 newtons. Okay. So you have an object here. It's sitting on the surface of a table, and someone is pushing down on the object with the 10 Newton force. In this example right here, how can we calculate the magnitude of the normal force acting between the two surfaces? So that's what we want to know, the magnitude of the normal force acting between the two surfaces. Well, guys, before I do this problem here, let me ask you guys a question. I want you guys to think logically here. Okay. So, in this situation right here, uh, uh, while the blue book is just sitting here and just sitting at rest, okay, you guys know how to easily calculate the normal force here because here the normal force balances gravity because it's at rest. Okay. Guys, can someone tell me what do you think would happen to the magnitude of the normal force between these two surfaces if I decided to push down hard on the book? What do you guys would think happened to the normal force? Do you think it would increase or decrease? What do y'all think? So if I'm pushing down on the book, okay, what happens to the magnitude of the normal force compared to when I'm not pushing on it at all? Um, um, it's not going to decrease. It would actually increase. Exactly. So the normal force would increase, right? Because as I push down on the book, I cause the magnitude of the normal force between these surfaces to increase. Um, and I'm gonna prove that to you guys now. How you know that the normal force is going to be increased? Because if you look, even though I'm pushing on the book, guys, the book is still at rest. It's not moving, even though I'm pushing down on it. So the normal force between these two surfaces actually increase. Um, Here's why. Well, and again, and by the way, guys, when I say it increased, I'm talking about relative to the situation in which I'm not pushing on it at all. Uh, So here's how you know that, guys. Whenever you're solving these problems like this, where I give you a situation like this and I tell you you have some external force involved and you need to find the magnitude of the normal force, the first thing that you want to do, you want to draw the other forces on the diagram. You want to draw the other forces that are acting on your object on the diagram as well. And then once you draw those forces, then it's easy to figure out what is the magnitude of the normal force. Okay, so guys, in addition to this external force here, there's also two other forces acting on this block. We know there's gravity, because gravity always acts on your object. So uh, there's gravity. And gravity always points straight downward. And of course, there's the normal force. There's the normal force from this surface here pushing up on this block. So there's the normal force. Okay. Now, in order to figure out the magnitude of this normal force, we need to figure out um, we need to figure out the force of gravity first. So force of gravity is equal to mass times 10. Okay. So if this block here is 5 kilograms, that means the force of gravity acting on it is 50 newtons. Okay. Now, how do we know the value of the normal force? Well, guys, let us think logically here. Even though there's an external force pushing down on this box here, the box is not moving. It's not accelerating. So that means the sum of all the forces must add up to zero. In other words, uh, in other words, the forces here must be balanced. So guys, in this situation right here, if it's not moving, that means all of my up arrows have to balance all of my down arrows. So my up forces have to balance my down forces. Notice I have two forces here that are acting downward, and I have one force here that's acting upward. So, uh, can someone tell me, guys, can someone tell me what has to be the value of this force here to balance these two down forces? Anyone? Yes, you guys got it. So that means in this situation, the normal force would have to be 60 newtons. The normal force would have to be 60 newtons, right? Because 10 plus 50 is 60 newtons, right? Because the one up force has to balance the two down forces, right? Because it's not moving, it's at rest, it's in equilibrium. Okay. Um, so hopefully that makes sense. there was something else I wanted to say. My mind just went blank. Oh, yeah. So guys, hopefully you guys can see that pushing down on the surface increases your normal force. Because think about it, guys. If this force wasn't here, if no one was pushing down on the surface, this normal force would be 50 newtons. But the moment you start pushing down on the surface, this normal force jumped up to 60 newtons. So pushing down on the object increased the magnitude of the normal force between these two surfaces here. Okay. So let's keep going. Let's do another example similar to this. So just to be sure you guys understand this point here. Suppose guys, I have a red box that has a mass of 8 kilograms. Okay. So it has a mass of 8 kilograms. And suppose there's a 20 Newton force currently, so a 20 Newton external force currently acting on the box right now. So 20 newtons. Okay. And if you have a situation like this, how can you figure out what is the magnitude of the normal force? Okay. So that's what I want to know. I want to know the magnitude of the normal force. Now, guys, remember what I said. In order to solve these problems here, whenever you guys see this on your assignment, here's telling you these are external forces involved here. But what you want to do, you want to draw the additional forces that you know are also acting on your object in order to define the normal force. And of course, there's two more forces acting on this object. We clearly know gravity is pulling the object downward. So gravity is pulling the object downward. And there's also the normal force between these two surfaces. So this table here is pushing up on the red box with a force. And again, that is our normal force. Okay. Now let's first figure out the force of gravity first. So remember, the equation for the force of gravity is equal to mass times 10. Okay. So if this block here is 8 kilograms, that means 80 newtons of force represents the force of gravity. And obviously that would be a negative because it's going downward. Okay. So, guys, remember what I said. If the box is not moving, our forces must be in balance. So all of our up forces should balance all of our down forces. So, guys, what has to be the magnitude of this force here in order to know what would balance these two forces? Yep. So in this case, it would be positive 100 newtons. So hopefully that makes sense to you guys. All right, let's do another one. I'm gonna kind of change it up a bit. Let us imagine, guys, that you have a situation like this where you have a box. Let's say we have a box here that has a mass of 15 kilograms. Okay. And let's say there's someone slightly pulling up on the box. So they're pulling up on the box with some force. And let's say, guys, let's just say this force here is 25 newtons. So in this situation right here, how will we calculate the magnitude of the normal force acting on? So how will we calculate the magnitude of the normal force acting between these two surfaces here? Okay. So guys, let us think logically here. We've already said that if I have, so I have my blue book here. We've already said that, if if I push down on the blue book, that increases the magnitude of the normal force between these two surfaces. Again, compared to when I'm not pushing on it at all. So pushing downward increases the normal force. But guys, what if I slightly pull up on the blue book? Just slightly. So if I'm pulling up on the blue book, what do you guys think happens to the normal force there? Does it increase or decrease? What do y'all think?
Decrease.
It decreases, exactly. Thank you, Courtney. So y'all got that? So pushing on the book increases the normal force between these two surfaces. Pulling on the book decreases the normal force between these two surfaces. So increases, decreases. Okay. So with that said, let us work out this problem now that you guys understand that conceptually. So going to this problem here, guys. So if I give you something like this on an assignment, remember, in order to correctly solve this, you want to draw the other forces that you know are acting on your object as well. So we have an external force. Someone is pulling this upward with the 25 Newton force. So now let us draw another forces that are acting. Okay, we know that for sure gravity is acting on the box because as long as the box is here on Earth, clearly gravity is pulling it downward. So for sure we know gravity is acting on the box. So there's a force of gravity. And also, guys, there's a normal force because the surface of this table here is pushing up on the box. So there's also a normal force acting. Okay. So in order to figure out the magnitude of this normal force, let us figure out what gravity is first. So the equation for the force of gravity is mass times 10, because I rounded 9.8 out to 10. So this mass here is 15 kilograms. 15 times 10 is 150 newtons. Okay. Now, guys, this box here is not moving. It's at rest. So that means all of these forces must be balanced here. So, guys, remember what I said. In situations where you're at rest, all of your up forces have to balance out with your down forces. Okay. So here, in this particular case, I actually have two up forces and one down force. So two forces that are pointed upward and one force that is pointed downward. So guys, in this case right here, someone tell me what has to be the magnitude of this force here such that if you combine these two forces, you get 150 newtons for your down force. Anyone? Come on, guys. Yeah, because y'all have to know how to do this. What has to be the magnitude of this force here? Because remember, when you add up both these forces, it has to equal 150. Guys?
125.
125. Thank you, Ramaya. It has to be 125. Right? Because the situation is in balance. The situation is balanced, right? So 125 plus 25, which is my two forces, when combined equals 150. So 125 newtons in this case right here represents the magnitude of my normal force. Okay.
Well, I have a question.
Yes.
Wait. Never mind. I know.
All right, you're good. Mm-hmm. Okay, so I'm going to pull up a worksheet, a PDF file, and I'm just going to go over a few of these concepts before I let you guys go, just so everybody is clear whenever you guys are working on this assignment later on. Hold on, guys. Let me clear these annotations. Give me just a second. Sometimes I forget to clear the annotations from the previous class. Let me do that now. Okay, guys, so you can see my screen now. Okay. So here I'm just going to focus on a few concepts here from this worksheet. Okay. So here it says, let's meet Jim. He's very slim. Draw and label all of the normal forces acting on slim Jim. Okay. So guys, let's start with situation A first. In situation A, it says Jim is leaning against the wall with 1 foot up. Okay, and we want to draw all the normal forces acting on Jim. Okay. So guys, if you want to know how many forces to draw in your picture, you look for all of your surfaces of contact. So here we have 2 surfaces of contact, so that means we're going to have 2 normal forces. So there's a surface of contact here because he's leaning against the wall. And then there's a surface of contact here because his foot is touching the floor. So that means we're going to have 2 normal forces. So let me draw out these normal forces. And of course, it's important that you guys know where these normal forces are pointed. Okay. Remember, we're concerning ourselves with the forces acting on Jim. So guys, if Jim is pushing against the wall, Newton's third law says that the wall pushes back on Jim. So we're solely looking at the forces acting on Jim. That means the normal force here will be pointed like this. So there's a normal force from the wall pushing on Jim like that. And then there's also a normal force here where the floor is pushing up on his foot. So there's a normal force that looks like that. Should have drawn that smaller, but you guys get the point. So there's 2 normal forces here. Okay. So, and that makes sense, right? Because he pushes down on the foot. I mean, his foot pushes down on the floor, and the floor pushes back on his foot. That's Newton's third law. So that's how your normal forces should look like. Okay. Now, guys, whenever you guys are working on these problems, look very closely at what it is, at the object that it's telling you to focus on. So, for example, if it told you to draw the normal forces acting on the wall, then that means you would draw the normal force acting in the opposite direction, like acting to the right, because Jim is in contact with the wall and he's pushing on the wall in that direction. But in this particular example here, it asks for the normal force acting on Jim. Okay. So even though we know there are normal forces acting on the wall and there are also normal forces acting on the floor, we are concerning ourselves with the normal forces acting on Jim. Okay. So let's look at B here. In situation B, it says Jim is leaning against the wall with both feet on the ground. So the question is, guys, how many normal forces do you guys think we have here? Look at how many surfaces of contact do we have. How many normal forces will we have here? Anyone? Come on, guys. How many normal forces will we have here?
Would it be 3?
Yes. Thank you, Courtney. We're going to have 3 normal forces because there's 3 surfaces of contact. So there's a surface of contact here. There's a surface of contact here. And there's a surface of contact here. So if we're looking for the normal forces acting on Jim, so the wall is pushing him like this. Again, I should have drawn a straight arrow, perfectly straight. There's a normal force acting on his foot here. And there's a normal force acting on his foot here. So solely looking at the normal forces acting on Jim, there are 3 normal forces. Okay, because there's 3 surfaces of contact. Make sense? Look at situation C. In situation C, it says Jim is standing on a table and pushing on the ceiling. Okay, all right, thanks, Anthony, for responding. Jim is standing on a table and pushing on the ceiling. So how many normal forces are we going to have here, guys? Yep, thank you, guys. It will be 4 normal forces. 4 normal forces. We have 4 surfaces of contact. There's a surface. The foot is in contact with the table here. It's in contact with the table here, and his hands are in contact with the ceiling here and here. So we're concerning ourselves with the forces acting on Jim. So there's a normal force pushing up on his foot like this. or the normal force pushing up like this on this foot here. So the table is pushing up on the foot. Now, guys, someone tell me, the normal force here that's acting on Jim's hand, what direction is it pointed in here? Do you think am I going to draw my arrow pointed up or down? What do y'all think?
Down.
Down, exactly, right? So hopefully that makes sense, guys, because that's logical. If Jim is pushing up on the ceiling, according to Newton's third law, must be pushing down on him. Right? That's Newton's third law. For every action, there's an equal and opposite reaction. So the ceiling itself is pushing down on his hands like this. So the normal force, remember, is always perpendicular to your surfaces of contact. So normal forces look like that. Okay. All right, let us just talk about a few more things before I end this Zoom call. Now let's look at number 2. Some of these situations we've already talked about. I just want to be sure everything is clear to you all. Okay. If a surface has to support more, it has to provide more normal force. Does the following increase or decrease the normal force? What does pushing down on an object does? We already talked about this. Pushing down on an object does what? It increases the normal force, right, between those two surfaces, right? Remember how I said that if you have a book, and if I push down on the blue book, that increases the magnitude of the normal force between these two surfaces. Okay, so we talked about that. What about setting another object on top of it? What would that do to normal force? Would it increase or decrease it? That should be kind of hopefully common sense. Guys, if you set another object on top of it, what is happening to the normal force between the two surfaces? Well, it should be obvious that it increases the normal force. Okay. What about friction? Does friction have any impact on the normal force? What do y'all think? So does friction increase, decrease the normal force, or does it do anything at all to the normal force? Does it have any impact at all on the normal force? Well, to help you guys make sense of this, let me explain something here. So, guys, consider this book. Yeah, Anthony, you're actually right. Yeah, you're right. It doesn't do anything. You're exactly right. Here's how you know that. Because guys, look. So right now we know there's a normal force between these two surfaces here. And the normal force, the white book is pushing back up on the blue book. Okay. Now, guys, that's a vertical force. Right now, the normal force is a vertical force. If I slide this blue book across the surface of this white book, there's now friction acting on the blue book. So there's friction between these two surfaces. Guys, is that friction impacting the normal force at all? Well, think about it, guys. Friction, as this book slides, friction acts along the vertical direction. Friction acts along the, friction acts along the horizontal direction. Okay. So friction acts along the horizontal direction. However, the normal force is pointed in the vertical direction. So it turns out that anything acting in the horizontal direction, any force acting in the horizontal direction won't have any impact on any force acting in the vertical direction. So friction does nothing at all to the normal force. So friction has no impact on the normal force. So I'm going to put an N there for nothing. Friction does nothing to my normal force. Guys, what if I have an object and I decrease the object's weight? What do you guys think? Decreasing the weight of the object, would that increase or decrease the normal force? What do y'all think? Yep, decrease the normal force. It's kind of like, guys, imagine that you had a little sister and your little sister is a lot smaller than you. If you step on a scale and she steps on a scale, Since she's way less than you, she's basically going to be pushing down with a smaller force on the scale than you are. So that means the normal force for you will be greater than for her. And it will be less for her compared to you, because she's a smaller weight. And obviously the scale will register that. The scale will measure a smaller weight for her, because she's pushing down less on the scale than you. So decreasing the weight of the object decreases the normal force. And we've already said this here, pulling up on an object does what? Pulling up on an object decreases the normal force. What about increasing the weight of the object? That should be obvious. Increasing the weight of the object increases the normal force. What about pushing sideways on the object? So assuming the normal force is a vertical force in that case, pushing sideways on the object would do nothing because that's a horizontal force. What about pushing down at an angle on the object? So if you're taking an object and you push it down at an angle, so even though you're pushing at an angle, you're still pushing downward. So there's some component acting downward, so that increases the normal force. Okay. So hopefully all of that makes sense. One more thing I want to look at here. I want to look at this situation right here. In each situation, if you have a roller coaster on a track, in each situation, well, at point A, point B, and point C, you have to figure out where is the direction of the normal force pointed in terms of the roller coaster's track pushing on the roller coaster itself. So if the track is pushing on the roller coaster, where is the normal force pointed? Okay. So guys, look at this surface here. So here, the surface is at an angle. So that means here the normal force is going to be pointed diagonal like that. Here, the normal force is going to be pointed straight up. So the track itself is going to be pointed straight up. The same thing for this here is going to be pointed straight up. So just keep that in mind, guys. Whenever your surface is at an angle, the normal force is pointed, diagonal at an angle as well. Any questions on the normal force? Okay. So that video link is in YouTube in case you guys want to watch that again, just to be sure those concepts are solidified. Because you want to be sure these concepts are solidified before the test on next week. Any other questions on the normal force? Okay, guys, as soon as I let you guys go, I'm going to make this assignment available in Schoology. Give me a couple of minutes.